The broadcast is now starting. All attendees are in listen-only mode.
Good morning, North America, and welcome to our external webinar for cutting tools. Today, I'm also happy to see some of the overseas attendees. So good afternoon to you whenever you're sitting. So I'm really excited to see that the number of people getting into this session, and we'll really appreciate your time. And I hope this is something you see value in. Today we will be talking about troubleshooting while using solid carbide drills. We all have been into that drilling a holes, breaking a drills, and carbide drills are not the cheap stuff. So we'll just make sure that you know all you need and you get the most out of the carbide drills. I have today with me Gary Kirchhoff, who is a state of the art in solid carbide drilling. So you cannot have a better guy to walk you through this one. So hope you have your coffee and enjoy this session. Gary, stage is yours.
Okay, good morning everybody, or good afternoon, whichever the case may be. This presentation will provide some helpful tips for using solid carbide drills in applications where it's not the usual situation for using solid carbide. While some people would make the switch down to cobalt or HSS drills when encountering these situations, sometimes you can stay with carbide drills to maintain optimal productivity, but you'll need to make some adjustments to the running parameters. Safety is everyone's responsibility. Always maintain a safe environment and be aware of exits in case of an emergency. When in the shop environment, follow all safety requirements that are set forth by the manufacturer, as well as the standards set forth by Dormer Pramet. When using solid carbide drills, always wear the proper eye protection, as chips can fly out of the machine and tools can break or shatter. We should always follow the production planning process as outlined here. The drilling tool selection procedure will follow this process and will include these 5 steps. Number 1, analyze the component you will be drilling. Number 2, choose the proper machine. Number 3, choose the right tool for the job. Number 4, apply the proper running parameters, coolant, etc. And number 5, troubleshoot and analyze the tool failure in order to optimize the operation. Today we will focus on step 1, analyzing the component, step 4, applying the tools, and step 5, troubleshooting. Of course, we are making the assumption that we already have a machine that is capable of running these tools at the proper parameters, step 2, and we know we will be using solid carbide drills, step 3, for this exercise. Stay tuned for future training webinars, as tool selection is a big topic on its own that could easily fill an entire training session by itself. The first part of this process is to analyze the component or workpiece. This includes a good understanding of what you are working with and what requirements you need to achieve in order to produce a good hole. First, you look at the various aspects of the material you are drilling. We classify materials in 2 different ways. AMG is application material groups, mostly used today for round tool selection, or ISO material classifications, currently used mostly for indexable tool selections. In analyzing the component, you must consider the machinability of the material, how the chips will form, and the hardness of the material. You also have to analyze the specifications of the holes you are drilling. This includes hole diameter, hole depth, and hole quality, and the many variables that will affect these specifications. These variables include the stability of the part in terms of thickness, or for a cylindrical part, the wall thickness if there's an ID and OD. The reach required, how far the drill must stick out of the holder. Good fixturing, this is a must for successful carbide drilling. And is the drill rotating or is the part rotating? In analyzing the component, you must consider the surface the drill will contact and how the drill enters the workpiece. One of the variables you will deal with from time to time is drilling on inclined surfaces. Using a solid carbide drill, there are some rules to follow to avoid drill breakage. If the angled surface is between 1 degree and 5 degrees, you should reduce the feed rate to about 1/3 or 33% of the recommended feed rate. If the angled surface is between 5 and 10 degrees, you should reduce the feed rate again to at least 33% and up to about 1/4, 25% of the recommended feed rate. In these situations, it is still strongly suggested to perform a centering or spotting operation first using a short spotting drill, which has the same or greater point angle as the carbide production drill. This will minimize the deflection due to the stub length and extend the tool life on your production drill. You should still reduce the feed rate on the spotting drill the same as you would if you were using the production drill because of the way it will contact the workpiece. If you encounter any angled surfaces greater than 10 degrees, do not use a solid carbide drill on this unless you mill a flat surface perpendicular to the center of the drill first. Another of the variables you will encounter is exiting on inclined surfaces. Using a solid carbide drill, you should again reduce the feed rate to at least 1/3 and up to 1/4 the recommended feed rate just before the drill starts to break through. As always, use the shortest drill possible, and that will also help with this scenario. Very steep angles can still cause chipping even with the reduced feed rate. Entering or exiting on irregular surfaces can also be a challenge. Using a solid carbide drill, you should always reduce the feed rate to 1/4 the recommended feed rate. Again, using the shortest drill possible will always help with this scenario. Once past the rough surface, the feed rate can be increased back to the normal rate. Take a close look at the drill periodically to see if the carbide is chipping so your hole quality is not compromised as the drilling operation continues. Entering or exiting on concave part surfaces. The rule of thumb for solid carbide drilling is to only do this if the part radius is at least 15 times the drill diameter. When entering or exiting on concave part surfaces, you should always reduce the feed rate again to 1/3 of the recommended feed rate. Again, using the shortest drill possible will always help with this scenario. If the part radius is smaller than 15 times diameter, you can try to reduce the feed rate even more, but that is really not highly recommended. When entering the part on a convex part surface, the part radius must be at least 4 times the drill diameter. In these cases, you should always reduce the feed rate to about 1/2 or 50% of the recommended feed rate. Again, using the shortest drill possible will always help with this scenario due to the stability of the shorter drill. As the part radius gets smaller than 4 times D, the drill will want to walk more on the surface, so this is not recommended unless a flat is milled on this surface first. When drilling through a cross hole, it is always best to reduce the feed rate to 1/4 or 25% just before breaking through into the cross hole. You should continue with this reduced feed rate all the way until you are completely through the cross hole. Once back at the full diameter past the cross hole, the feed rate can be brought back up to the recommended feed rate. When drilling stacked plates, it is often not necessary to reduce the feed rate if the plates are clamped tightly together and the gaps are eliminated. If small gaps remain between the plates, industrial paper shim stock can be used between plates to level out the irregularities and dampen vibrations. If gaps are present, this can cause drill breakage when a slug is pushed out at the exit and it becomes lodged between the plates. In these cases, the slug stays at the front of the drill and rotates with the drill as the drill feeds forward. This slug will push against the next plate and spin, preventing the drill to cut. When the drill continues to feed without cutting, this causes the drill to break because it is no longer cutting any material. Of course, if the gaps are large enough to allow the slug to eject out of the way, this can also be successful. Spacers can be used between plates to increase the gap size, which can allow the slug to eject properly. It is never a good idea to use a 2-flute solid carbide drill for coring operations. In this case, the chisel of the drill is not doing any of the work and no chip breaking will take place. The chips created will be long stringers which can wrap around the drill body or get clogged in the flutes, causing drill breakage or damage to the part. Use of a core drill or a solid carbide 3-flute drill is always recommended in cases like this. So we will be skipping these steps today because we already have determined the machine to be adequate and the tools being used are solid carbide drills. We have also determined the proper running parameters based on the material with adjustments as necessary according to the previous slides. As I said earlier, tool selection will come up as a topic for the future. So, on to troubleshooting and failure modes for solid carbide drills. Number 1, built-up edge. This is a common problem when drilling softer steels, non-ferrous materials, and stainless steels. Listed here are some of the causes for built-up edge. Cutting speed and edge temperature is too low. Negative land on the cutting edge is too large. No coating. Percentage of oil in the cutting fluid or concentration of synthetic fluid is too low. And the solutions for this can be to increase your cutting speed or use external cutting fluid. Use sharper cutting edge geometry. Use a coated drill to increase the lubricity and increase the percentage of oil in the cutting fluid or increase the synthetic percentage. Chipping on the cutting edge corners. Here are some of the causes. Unstable fixturing, runout is too large, intermittent cutting, insufficient cutting fluid, which causes thermal cracking, unstable tool holding. Some of the solutions for this: check your fixture, check the radial runout. It has to be less than 0.0004, 0.0004 of an inch TIR with solid carbide drills. Any more than that should be corrected with a more accurate holder or a new collet. You can lower the feed rate, you can check your cutting fluid supply, and you can check your tool holder. This PDF presentation is attached so you can use it as future reference tool for troubleshooting and analyzing the component. All these different causes and solutions, it's impossible to remember all that. So this should serve as a nice tool for going back to refer to these different situations. Excessive wear on the cutting edges. Check your running parameters to be sure the drill is operating at recommended speeds and feeds. One of the causes for this is cutting speed is too high, the feed rate could be too low, the surface is too soft, or there is a definite lack of cutting fluid. Some of the solutions would be to lower the cutting speed, increase the feed rate, add a coating to increase the surface hardness on the tool, and check for proper cutting fluid supply. Chipping on the cutting edges. The most common cause for chipping is bad fixturing or extremely hard workpiece materials. Some of the causes: unstable conditions, maximum allowed wear is exceeded, in other words, you've let the drill go too long, surface is too hard. Solutions: check your setup, replace the drill sooner. Always have a replacement plan where you're pulling that drill prior to the total failure of the drill. Try a different coating or try a different geometry. Excessive wear on the circular lands. Start by rechecking the runout at the drill point. This can sometimes change as the cutting forces change during the operation. Remember, again, any runout in excess of 0.0004 TIR is too much. So, as I said, the cause, your TIR is too large, your cutting fluid mixture is too weak, the cutting speed is too high, or the material is just very abrasive. Solutions: check the radial runout again. Use neat oil or a stronger percentage of the emulsion coolant. Lower the cutting speed or add or change coatings to increase the surface hardness on the tool. Excessive wear on the chisel edge. Most often, the cutting speed is too low or the feed is too high. Chisel edge could also be too small in these cases. Some of the solutions: you can increase your cutting speed, you can lower your feed rate, and you can check the dimensions on the tool, make sure the tool is made to spec. Plastic deformation. This is normally caused by too much heat building up at the cutting edges. As we've said over and over in our webinars, the speed causes heat, and heat will kill your tool. So some of the causes: again, cutting speed or feed rate is too high, not enough cutting fluid supply, or lack of surface hardness on the tool. Solution: lower the cutting speed or the feed, increase cutting fluid pressure and volume, use a better coating or add a coating if the drill is uncoated. Drill breakage, also known as catastrophic failure. Letting any of the problems mentioned go too long without being corrected can result in drill breakage. This can be caused by ignoring any or one of these causes or a combination of two or more of these causes. Causes, again: insufficient clamping, the workpiece is moving, unstable cutting conditions, insufficient spindle power, chip packing, your feed rate is too high, or just excessive wear. You've let the tool run too long. Solutions: stabilize the workpiece and the drill, improve the clamping, check your cutting data, check the machine, adjust your cutting data and fluid supply, lower the feed, and check the wear more frequently. Thermal cracking. If the coolant is sputtering, the temperature of the drill can go way up, and a splash of coolant will quench the carbide, causing cracks. I like to relate this to letting a piece of glass heat up red hot and then dipping it in water. It's gonna crack and it's gonna break. So some of your causes, again, this is one of your causes. The only cause is inconsistent cutting fluid. Your solution: check your cutting fluid supply. Fill the cutting fluid tank so you don't get the sputtering when it starts to suck air. Clean the sludge from the tank and the coolant lines. Sometimes the sludge will get into the coolant lines and you'll get intermittent coolant delivery. Oversized holes. Your speed is either too low or your feed is too high, usually. Your bad fixturing can cause this as well. If the fixturing is allowing the part to move, this can also cause this. Or, again, too much run out on the drill. Increase your speed or reduce your feed. Correct part clamping and make sure that part is extremely rigid. And eliminate the run out. Again, less than 4/10 of an inch is necessary in carbide drilling. Undersized holes. This can be caused by a lack of coolant, your speed is too high or your feed is too low, or your drill is undersized. So improve your coolant direction and the volume of coolant, decrease speed or increase your feed rate, check your drill diameter and your tolerances, make sure everything is to spec. And holes out of round. Too much run out, again, can cause this situation. Bad fixturing can also cause this, or chip packing can cause this situation. So you're going to want to eliminate the run out. Again, always be sure your run out is less than 0.0004 inch TIR. This is necessary, and even during the operation that can change, like I said earlier, because of the cutting forces. Correct your part clamping and your rigidity. Check your feed rate and or change your flute form. As mentioned several times now, the runout is extremely critical when drilling with carbide. While using a Weldon holder or a drill adapter may be adequate when drilling with indexable drills, and using a conventional drill chuck is adequate for high-speed steel or cobalt drills, these types of holding methods are not recommended for solid carbide drills. In order from best to worst for solid carbide drilling, shrink fit holders, hydraulic chucks, power chucks, and very good quality ER collet chucks are your best options for holding the drill with the least amount of runout. As you can see in the diagram at the bottom of the page, uniform contact around the tool shank is necessary. Drill adapters and Weldon holders will force the tool slightly off center because the point of contact is on one side only. Vibrations and runout beyond 0.4 TIR are your worst enemies in solid carbide drilling. A beat up or bad collet, a damaged tool shank, or a damaged holder can ruin an otherwise perfect setup. As illustrated on the previous slide, shrink fit or hydraulic chucks offer the most accuracy in solid carbide drilling. Next, I will provide a brief overview of our Force X solid carbide drilling program. Back in 2007, we introduced an assortment of dormer multi-purpose solid carbide drills called MPX drills. These drills for 3 times diameter and 5 times diameter drilling depths have a common and straightforward design with a 140-degree split point suited to drill a broad range of materials. The strategy behind the development was to come up with a drill to compete with the low-price solutions offered by some of our competitors. In 2015, the range was expanded by adding the R459, which was developed as a high-performance solid carbide solution for 8 times D deep hole drilling. Although the original 8 times D R459 drill belonged to the same family of MPX drills, its features and customer benefits were higher than those of the earlier developed MPX drills. To improve our competitiveness in 3 and 5 times drilling, we needed to upgrade these drills to the same level of performance as the 8 times D R459 design. So there was a boost in performance for the 3 times D and the 5 times D drilling by going to this R459 type design. The challenges set for the development of the new solid carbide drills for the 3 and 5 times D was to come up with a new geometry. This new geometry provides a high level of performance in a wide variety of work materials. We'll achieve the same level of productivity with 3 times D and 5 times D drills as can be reached with the 8 times D drills. Ensures a reliable drilling process with consistent forces along the full drilling depth capacity of each drill. And will also perform well in light-duty machines due to the reduced cutting forces. With the Force X introduction, our assortment of solid carbide drills will cover a diameter range of 3 mm to 20 mm for the 3 and 5 times depths, and 3 mm to 16 mm for the 8 times D depths. We also have the fractional wire and letter sizes in 3 and 5 times D, which I'll get into in a few minutes. To emphasize the higher performance levels, the newly designed product family was rebranded as Force X, a new range of versatile solid carbide drills designed to provide an excellent level of performance with outstanding economy. Along with this design change, we are expanding the 3 and 5 times D ranges to include the wire gauge and the letter sizes. Force X R457 and R458 drills. R457 cool-it-through design and R458 solid construction are solid carbide drills for drilling depths up to 3 times diameter in a broad range of materials. The size ranges are from 3 mm to 20 mm in our metric sizes. 1/8 inch to 3/4 inch in our fractional sizes, wire gauge sizes from number 1 to number 30, and letter sizes from A through Z. The features and benefits of this whole family are micrograin carbide. This provides an excellent combination of hardness and toughness suited for high-performance drilling in a broad range of materials, resulting in high wear resistance and longer tool life. We have a multi-layer TiAln coating, which improves the cutting-edge stability and outstanding wear protection, retaining high hardness at high temperatures, prolongs tool life, and increases productivity. Our patented CTW, continuously thin web flute construction, provides a very strong web design, helping to reduce the drilling forces with high feed, and ensures good chip control and improved process security. As an additional feature, the CTW also allows for easy regrinding. Our edge preparation, it's a consistent edge prep which protects the cutting edges and prevents premature chipping and flaking. This, in combination with the special point geometry and the CTW flute, ensures precise centering and low thrust forces. And through coolant for better chip evacuation and long tool life on the R457 series. Force X R453 and R454 drills. R453, which is coolant through, and R54, which is solid construction, are solid carbide drills for drilling depths up to 5 times diameter, again in a broad range of materials. Again, the sizes range from 3 millimeter to 20 millimeter, 1/8 to 3/4, wire gauge from number 1 to number 30, and letter sizes from A through Z. Features and benefits, again, include the micrograin carbide, multi-layer coating, CTW flute construction, edge preparation, and the through coolant design for the R453 series. Force X R459 drills. The R459 is a solid carbide drill with through coolant only for drilling depths up to 8 times diameter, again in a broad range of materials. On this range, the sizes are metric and fractional only, from 3 to 16 millimeter metric and from 1/8 to 5/8 fractional. Again, we feature the micrograin carbide, the multi-layer TiAln coating, the CTW flute construction, the special edge preparation, and through coolant on this entire series. This concludes our third external webinar for 2018, Solid Carbide Drill, Troubleshooting, and Dormer Force X Drills. Join us again next month for our continuing series of external training webinars. Thank you and have a great weekend.
Thank you, Gary. As let's see, we have any questions here? We got yes. So there is a question. What increments do the metric drills commonly come in?
It varies. Sometimes it'll be every 0.1 millimeter. Sometimes there'll be some other sizes in between. So you really have to check the offering. There are different types will have different requirements based on our market needs.
Is a packing cycle ever recommended with carbide drills?
No. With the Force X drills and for that matter the MPX drills, the packing is not recommended. It will force the drill to sometimes work harden the material, and it can lodge chips in the bottom of the hole.
Good. That was so far the questions we received. If you have any other questions, you can post it now or later to our mailbox. You will receive we will have the troubleshooting guide, as Gary said, available on our website www.doverpramet.com or delivered through your emails you use for registering. One thing to mention, all our previous videos are available on either our website in our knowledge base session or on Dover Pramet YouTube channel. next session, looking forward to see you again or talk to you again in about 1 month from now, last Friday in April. There is no need for you guys to register again because your registration is available still and valid. So you will receive the reminder, and the agenda or a flyer will come out on our website the next week, and also through the socials, Facebook and LinkedIn, as you're following us. So thank you for your time. Hope this was valuable, and yeah, enjoy a lovely weekend wherever you are. Talk to you next time. Bye.